All right, 3.3, we started last time. We had taken a look at 3 different types of formulas, double angle, power reducing, and half angle. And these are on a variety of different slides that I have. So these are our double angle formulas. They all say what happens with our 3 basic trig functions when we do twice the angle. And then we had our power reducing ones. Our power reducing talk about how we can take powers of 2 and make them with that's not the word I want. Reduce them to have only powers of 1. And then the third set were the last ones we had done right here, our half angle formulas. And in our half angle formulas, we have half of the angles that are listed instead of double the angles on the first slide. And the thing that we have left, or the 4 problems that we have left in this section, all have to do with verifying identities that involve these types of formulas. So we're going to take a look at a few different problems here at the end of this section, 7, 8, 9, and 10. And so we're going to verify each identity. Now, we had talked about before, you can work on the left side or you can work on the right side. Sometimes it's a very natural choice and you're like guaranteed definitely going to work on that side. And sometimes it's a little bit less clear and you can choose whichever you'd like. This section actually starts in with some of the things that you're going to need to do in terms of being able to do the algebra gateway that we had mentioned next class period. And I'm going to work with the right-hand side because I think it leads right nicely into some of the algebra things that you're going to want to make sure that you remember how to do. So if you take a look at the right-hand side, what I hope that you notice on top is that you have a secant squared and a secant to the power of 4. So it's very much like having x squared and x to the 4th. So I could actually give you something like x squared plus x to the 4th on the gateway on Friday or Wednesday, and I could say factor it. And I think that you probably would know how to factor that. There's 2 different pieces, and they have both in common an x squared, so we'd pull the x squared out in front, and we would be left with, 1 plus, and then an x squared. Nod your head if that looks familiar. Okay, so that's the kind of thing, one of the pieces that will be on the algebra gateway on Wednesday, is things where you're looking for a common factor and you're pulling it out. Now, if you take a look at the numerator on this one, clearly we don't have x to the 4th and x squared. We have secant to the 4th and secant squared, but the process still works the same way. What do they have in common? Secant squared. So we're going to pull a secant squared of x to the front, which leaves us with 1 plus secant squared of x. Okay, factoring. The second component on bottom, right, is also factoring. Let me change it into its version that's the analogous version in algebra. I'm going to change all of these into saying x squared or x to the 4th. So we have, that looks funny, 2 and then plus secant squared, so now plus x squared, minus secant of the 4th, so that's x to the 4th. Okay, that's the equivalent of what we have here. And if I were to factor this, the x to the 4th would give me an x squared at the end of both of them. Because it's negative at the end, one of them's negative and one of them's positive. Okay, all of this should be definitely reviewed. Like you've seen it in at least 3 classes in your career as a student. You saw it in Algebra 1, you saw it in Algebra 2, and you saw it in some sort of a pre-calc or college algebra, Algebra 3, math analysis, whatever the course was you took of that equivalent. You've seen it there too. Now, I need to have a 2 and a 1 at the beginning because 2 times 1 is the only thing that's going to multiply to give me 2, right? So I have choices. I can either do 2 and 1 like this, or I can do 2 and 1 like this, and I just have to figure out which one works for the pieces that I've been given. And I do that by taking a look at the inner and the outer terms. So if I do the inner terms here, I've got negative 2x squared. And if I do the outer terms, I have positive x squared. So if I add negative 2x squared and positive x squared, what do we get? I get x squared. Is it positive or negative, though? It'll be negative. Do I want it to be negative? I don't. So when that's the case, you can either swap the signs, right? The negative and the positive can switch, which is fine. Or in this case, we could switch the 2 and the 1 because those are the last things we put in. I'll switch the signs because in general, that's actually the method that works for all things. So I'll do it in this one. If I do that, now what happens is that instead of having a negative 2x squared here, I have a positive 2x squared here. Instead of having a positive x squared on bottom, I have a negative x squared on bottom. And now it adds to the right values, right? Okay, so this is the algebra piece that mirrors what I'm doing over here with this trig. So we're going to take this and we're going to do the same thing. I need to have a 2 and a 1, right? That's what multiplies to give me 2. Secant squared, and secant squared will give me secant to the 4th. Please make sure that you're remembering that the x has to be there. You can't just write secant squared, even though I sort of verbally say it that way, right? Secant squared of x. And then my signs need to be careful, right? They match the ones that I was just doing, so it'll be a, well, I put them in the other order, so let's just switch these so they match. I had this as a 1 at the beginning, a 2 at the end, and then I had plus and minus. It doesn't really matter, but I just wanted them to see that that matches to the other ones. And you can check, right? So if we hadn't just done this with the algebra component, we can check it like this. This gives me 2 secant squared of x and minus secant squared of x. And if I take 2 secant squared minus 1 secant squared, I get 1 secant squared, which is what I was wanting to have in the middle of this particular problem. Now here's the deal. That's all well and good, but there's actually a little bit of a cheat step in this particular problem and in many problems like this as well. The goal is that you want something on top to reduce with something on bottom. Do you see the one that will reduce in this case? Yeah? These two, let me erase the yellow that I've been working with. Oops, try again. This piece and this piece are identical, right? Okay, so as you're taking a look at making sure I get my signs in the right place or my 2's and my 1's in the right place, you know that this is going to have something cancel out. I mean, like, that's the whole point, right? So it gives you kind of a clue as to what you want to have the factor be on the bottom. If I know that my goal is to get it to cancel with 1 plus secant squared on top, then there's probably going to be a 1 plus secant squared on bottom. And then if I fill in the other pieces with the 2 and the minus secant squared, I can check to make sure I have them in the right order to multiply out. I do. These will cancel. So what am I left with? Well, I'm left with secant squared of x on top and 2 minus the secant squared of x on bottom. Now, that's not exactly the left-hand side still. Agreed? But it's definitely a reduced version. It's cleaned up a bunch. So what we're going to do next is we're going to turn them into cosines. Okay, sines and cosines come into play a lot, changing them. So let's change those. So this would actually be on the right-hand side, 1 over cosine squared of x over 2 minus 1 over the cosine squared of x. So part of the problem with this problem is that I don't have a form for secant of 2x, right? If you go back to our very first slide, and you've got your list there, so you can get there faster than I can probably, but there's no secant 2x on this, right? But I do have cosine of 2x, correct? So if I have, and I have 3 versions of it, I have 3 versions of cosine of 2x, or 2 theta in this case, right? And if I could get any one of these flipped upside down, that would be secant, right? Because secant and cosine are reciprocals. So if any of these versions of cosine 2 theta were on the bottom with a 1 on the top, then I would actually have what I'm looking for. Okay? In other words, it's equivalent over here to say that secant of theta, 2 theta, excuse me, is equal to 1 over any version of those 3 versions of cosine 2 theta. That's what I'm trying to achieve. I'm trying to achieve a denominator that looks like one of these expressions of cosine. So let's come back over here and continue on the process because we're not that far away. We have all the cosines in there now, but we've got fractions inside of fractions, which we've discussed before is not a very pretty thing to have happen. So we're going to multiply by the denominator of the fractions. The denominator of these fractions are exactly the same. And I multiply every term, or you can think of this as distributing through like this, right? So I'm going to write mine over here. So on top, what happens? The cosine squareds just cancel, so I'm left with a 1. Right, Jamie? Yep. Okay. On bottom, the left-hand side, those just get multiplied. So this is 2 cosine squared of x. And then what happens on the right? They cancel again. But they cancel to a 1. Right, Beck? Okay, so here when we say cancel, sometimes when we say cancel, we think 0. This is 1. These multiply to 1. So I have minus 1 at the end. That's actually a really good thing. What is that that's on bottom now? It is one of our 3 double angle identities, isn't it? It's this one right here. It is cosine of 2 theta in a different version. So over here, I'm going to make you guys sick passing back and forth through my slides today. I have cosine of 2, and it's theta, but ours is x, so 2x on bottom. 1 over cosine of 2x. But what is 1 over cosine? It's secant. This is equal to the secant of 2x, which is exactly where I wanted it to end. These are now equal, and I'm done. Okay? There's a lot going on in that problem. We started with factoring, something we haven't really done a lot with here, right? And then we used that double angle in a way that was sort of backwards of how it's written. We worked with the right-hand side moving to the left-hand side. Okay, let's try some more. All right, so taking a look at this one, again, we typically try to work with the messier side first because it cleans up as we go. So which side would you say is probably the messier looking side? The right-hand side looks a bit messier. Could you work with the left-hand side and make it work? Probably. But the right-hand side's a good place to start here. It's a reasonable start. So as we're taking a look at the right-hand side, what I'd like for you to notice is that some of the angles, and it's actually true from the right to the left, some of the angles are double angles, right? These 3 are doubles. And then some of the angles are singles. Y'all notice that? Okay. We need them to all match, right? Like they can't be a mixture of things, right? Like we need them to match in some way. And while eventually we want it to look like what's on the left with the double angles, it might be easier to work with what's on the right in single angles for the moment to clean some things up. So that is how I'm going to start on this particular problem. Because right here, this sine of 2 alpha, we have a formula for that. So somebody flip back or look on your other sheet. What is the sine of 2 alpha? Yep, 2 sine alpha, cosine of alpha. Okay, did everybody find that okay? All right. Now you might look at that and think it made it look a little bit worse. It did kind of make it look a little bit worse. But we have some components that match now. Okay? So a lot of what we're going to see happening in these sections is going to hinge on that algebra that we're working with, including factoring. Half of your quiz on Wednesday is going to be factoring, and the other half is going to use some factoring as well. So as you're taking a look at the right-hand side, what can we factor out of both pieces? Somebody tell me something you see. Okay, there's a cosine alpha. Does everybody see that? That's in both pieces. What else do you see that we can factor out? There's 2 more things. A 2. There's a 2 here and a 4 here. They both will factor out with a 2. What else? Better be sine. That's all that's left, right? Okay, so there's a sine alpha here, and there's 3 of them here, so I'll pull 1 of them out. So we're going to pull out a 2. We're going to pull out a sine of alpha, and we're going to pull out a cosine of alpha. What does that leave from this first piece? 1, right? I've pulled it all out. I've factored it out. It's kind of like dividing it out. I have a 1 remaining minus what remains from the second piece. Good. 2 and then sine squared of alpha. That's factoring, but with trig. Okay? Now that's actually kind of cool, because if you take a look back at those double angle formulas we had on the very first slide, what is the part that's in parentheses? We'll start with that. That's one of our 3 versions of it, right? Of cosine of 2, and it was theta on the screen. It's alpha on this screen, right? So cosine 2 alpha. What is 2 sine alpha cosine alpha? That is, no, careful, look back again. What is 2 sine alpha cosine alpha? Yeah, it's the sine. of 2 alpha. You did them backwards. That's okay. So the first piece is sine 2 alpha. The second piece is cosine 2 alpha. And what do you find? We're there. We're done. Okay, things collapse very nicely on that one. All right. Let's take a look at this one. So directions stay the same. Verify the identity. It says cosine of theta, and it's 1 minus tangent squared of theta over 2. And then I've got 1 plus tangent squared of theta over 2. So we have some half angles now, right? So those slides are not too far back. The half angles are right here. And both of the half angles that are mentioned here are down here at the bottom with the tangent of alpha over 2. Now, if you take a look at the one that we're working with here, it's asking us to square the tangent value. Do you guys see that? It says squared, correct? The fact that it's squared means that the one over here that's the easiest to use, because there's 3 versions of tangent of alpha over 2, right, is the first one. The first one's a square root, and squaring square roots are very friendly. So we like the first one. Maybe normally we don't because there's a square root, but in this case we do because the square root is going to cancel with the squared. So we're going to use that first version on this one. So I have 1 minus. And then this is supposed to, I know it's plus or minus. In fact, I'll even write it in here, but it won't end up mattering. It was 1 minus, you'll have to tell me if I've got it right from my notes. I have 1 minus cosine alpha over 1 plus cosine alpha. Is that correct? Okay, great. And then that's squared. All of that is over 1 plus, and it's the same thing, plus or minus the square root of 1 minus cosine of alpha over 1 plus the cosine of alpha. A lot of these things get messier before they get cleaner. Okay, so do not fear the mess. It will all come out clean in the end if we've got the right pieces canceling, and we do here. I went ahead and put the plus or the minus in here, but do you see why they don't really matter? What happens when you square things that are positive or negative? It cancels, right? Everything becomes positive when it gets squared. So feel free to just leave the plus or minus off on this. That would be perfectly reasonable because it will cancel itself out. Also, the square root and the square cancel, which is what we talked about beforehand, right? So I'm going to have 1 minus, right? That's coming from here. And then I have 1 minus the cosine of alpha over 1 plus the cosine of alpha. And all of this is over 1 plus, and it's still fractionally 1 minus the cosine of alpha over 1 plus the cosine of alpha. Yes?
In my mind, I would think that the 2 fractions would cancel. Why would they not?
It's a really good question. I'm going to give you a number of examples to show you why they don't cancel. Let's say you had 1 plus 2 over, we'll go with 1 minus 2. I think sometimes you can create examples that actually work. Hopefully this one won't. I'm just creating it, so we'll see what happens. So if you have a piece that matches perfectly, then the idea would be that these 2 would cancel. That's what you're sort of looking at and saying, hey, look, those fractions look the same. They should cancel. Then you would have to say, okay, well, how did they cancel to? Well, let's say they cancel to 1. Okay. You can cancel to 1. You can cancel to 0. Neither one of them is going to work. So we're going to end up getting a problem because this is going to give me 1 plus 1 on top, and now I have 1 minus 1 on bottom, which is 0, and I have 2 over 0. But this is not 2 over 0. This is 3 over negative 1. So you can't cancel individual terms in fractions, but you can cancel factors. So if we were able to pull something out as a factor in front, where it was multiplied by the pieces, then we would be able to. But we can't cancel terms. Okay, I'm really glad you mentioned that because that is it's like an innate thing we want to do. We see something that looks alike and we want to just like, bam, bam, it's gone. We can't always do that. We have to do that with care. Okay. However, the little denominators do match, right? It's much like an earlier problem that we had. They're just messier. So the little denominator is 1 plus the cosine of alpha. So we will multiply by 1 plus cosine alpha over 1 plus cosine alpha. Now I can do this because this is multiplying by the number 1, right? But I want to make sure that it's being multiplied to all of the pieces. So I'm going to shift this over to give myself some more space. I know that's sort of cheating because you can't really do that on your paper, but what ends up happening is I want to multiply all four pieces, the first two ones and the last two fractions, by that 1 plus cosine of alpha. Now, in the last two fractions, these, of course, cancel. That's the whole point, right? So those little denominators are canceling out. Multiplying by 1, that's straightforward enough. I'm just going to get 1 plus the cosine of alpha. And then I have minus. The first numerator is 1 minus cosine of alpha, or the top numerator, I should say. The denominator, I have a 1 plus cosine of alpha. And then I have plus, and I have 1 plus the cosine of alpha. Okay, I don't have any little denominators. There's still a fair bit of mess, right? I mean, it's getting better. This negative does need to distribute through right here. So I'm going to get a negative of this and a positive of this. I'm going to try and do it one step so I don't have to keep rewriting things. So I have a positive 1 at the beginning here, and I have a negative 1 here, which means the ones are going to cancel on the top, right? Okay. And then I've got a positive cosine of alpha and a positive cosine of alpha, so there's 2 of those. So I have 2 cosine of alpha on top. Everything's addition on bottom, so everything is going to combine. I wrote something down wrong. What did I write down wrong? This. That should be a minus sign. If you wrote it down wrong with me, make sure you fix it. It was a minus to start with right here. I recorded it incorrectly. Okay. Denominator, everything's addition except that last minus cosine. So I have 1 plus 1 here and here, so that's 2. And then what happens to the cosine alphas? They cancel, they add to 0, right? So in very much the same way that this one and this one added to 0, this cosine alpha and this negative cosine alpha add to 0. And what happens then? Yeah, I can cancel out the 2's. And lo and behold, that's exactly what I have. Oh, and I've got alphas everywhere instead of thetas. I'm so sorry. We can fix them all real quick. You should all say theta. That's what happened on your last quiz to me too, is that I had a wrong sign on, or a wrong angle on one side. They're all thetas. Sorry, the formula itself on that one had an alpha, which is what led me to do that. Okay, that's what I wanted, right? I wanted it to say equals cosine of theta at the end. It now does.
Where did the top 2 come from, that cosine and theta?
Because when I add cosine and cosine, I have 2 cosines. Yep. Good questions, good questions. Anything else to clarify that on this one? These are equal. Okay, we got one more verifying identity. One of the things that people often don't like about verifying identities is they're messy. And I think that's a fair statement. They are messy. They're kind of ugly. One thing that I hope that you do find valuable about them, though, is that you always know the answer. Right? This is not a mystery. Like, where am I trying to get to? What am I trying to end at? I know exactly what I'm trying to get to. It's the other side that it was given to me. So when I look at, say, this one right here, it may be ugly and so forth, but I'm not trying to figure out what is x, right? I'm just trying to make one side look exactly like the other side, which means I know the answer that I'm looking for. I'm just trying to figure out how to get there. So again, if we're looking at the messier side versus the cleaner side, which side would we be most likely to attempt to start with? The left-hand side on this one, right? Because there's some addition and subtraction. The right-hand side is a single expression of trig, right? Cotangent. All right, so taking a look at the right-hand side, we have the tangent have a half angle. So the tangent half angle formulas down here, there's 3 of them. I don't think we want to use the square root one this time. Right? There's no squaring going on, so that's not a very helpful place to start. The second one or the third one are probably about the same. I mean, like, look at them. They look almost identical, right? My notes have the first one of those 2, so I'm going to use that one, not because the second one's any worse, but just that way we make sure if I make a mistake, I can see what my notes have on there. So feel free to use the second one if you'd like, or the third one. I'm going to use the second one, okay? So I'm going to use the sine of alpha over 1 plus cosine of alpha, and our angle is x, and we'll actually write down the x's this time. All right, so the tangent is actually sine of x over 1 plus the cosine of x, if I use that version. Okay, is that all right? Okay, so then cotangent should be the same thing but flipped upside down, agreed? Okay, and that's fine. We can take this and flip this upside down if we would like, but I'd like for you to take a look at a neat little trick that we could use. I used the second formula for tangent, but the third formula for tangent looks very similar to the second one if you flip it upside down, doesn't it? If I take this version and I flip it upside down, it almost looks the same as the other one. Agreed? Okay, so I'm going to actually use this version for cotangent and flip it at the same time. Again, not the only thing you could do, but it's kind of a nice way of doing it. So over here, I'm going to use the second version, the third version of the tangent formula, flipped upside down, which gives me sine of x over 1 minus the cosine of x. Now the denominators are not the same, right? They're not, but they're very similar. In fact, what we're going to do now is we're going to get a common denominator, and to get a common denominator, we're going to multiply the denominators by one another. And this actually leads into another really nice factoring thing that I'm going to remind you of when we get there. So we're going to multiply this by 1 minus the cosine of x over 1 minus the cosine of x. And the other one is going to be 1 plus the cosine of x and 1 plus the cosine of x. And it's still equal to the right-hand side. Remember, we're moving down the page, not across the page, because the across the page piece is what we're getting to. Like that's the goal. All right, very good. So in the numerator now, if I distribute this through, I have sine x minus sine x cosine x. And then over here, I'm going to distribute the negative sine x through here. So I have minus sine x and then minus sine x cosine of x. Okay, the denominators in their algebra form look like this. I have 1 minus cosine x and 1 plus cosine x. So if I multiply those as 1 plus x and 1 minus x, we encountered this last class period. This is actually a form that cancels out the inner terms and the outer terms. This is positive x and minus x, right? Plus and minus, they cancel. So these are called conjugates. Shake your head if you remember me saying conjugates last time. Hope so. These are conjugates, and they have the nice feature that when I multiply them, I just get the first term squared. 1 times 1 is 1. The last term squared, x times x is x squared, with a subtraction sign in between. Why do I mention this in terms of factoring? Because if you start right here and you factor it back out like this, do you know what the name of that is? It has a very specific name. Do you remember it? Very close. It's differences of squares. So this is a difference of squares formula. So this is another thing that you could see show up on your gateway on Wednesday, is something that looks like this, where you have to recognize 1 and x squared, in this case, don't have anything in common to factor out, like that earlier one we did. But they do have a differences of squares formula. The first piece is something squared, the last piece is something squared, and there's subtraction in between. Okay, cool. So over here, following that same format, the first piece is squared is 1. The second piece squared is cosine squared of x. And there's subtraction in between. Okay, let's look at the numerator. What things cancel out and combine? What do you see? Okay, sine x and negative sine x, those cancel. And what remains on top can be combined, right? It's negative 2 sine x cosine x on top. And the bottom looks suspiciously like something that's on the gateway that you're still working on, doesn't it? What in the world is 1 minus cosine squared equal to? It is, but I'm thinking in terms of an identity. What other identity could we use here? Do you know, Reese? Not sure? The Pythagorean identity. Very good, JC. So there's a Pythagorean identity that says sine squared plus cosine squared equals 1. Y'all remember that one? Yeah? Did we already forget our gateway stuff that we did that you guys did so well on? Hope not. You're going to need those things. If we subtract the cosine x to the other side, we can see that the sine squared of x is equal to 1 minus the cosine squared of x, right? That denominator is really just sine squared of x. So what do you notice? Compare top to bottom. What can simplify? The sine x on top will simplify with one of the signs on bottom. So what I'm left with is a negative on top, a cosine of x on top, and then a sine of x on the bottom. Basic formula then, right? I do, thank you. Left my 2 out, problem. Definitely need that. Cosine over sine. It's one of our identities. That is cotangent. So the negative and the 2 stay, and then this piece is cotangent. And lo and behold, that was exactly what we were working toward. Okay, so what happens if you get in the middle of one of these and you're like, this is not going anywhere? Well, or maybe you're working in circles. That happens sometimes too. Then it might be a time to look back and see, was there a different way I could have approached this? So on this one, I chose the second formula for the tangent, right? And I'm working through this, and then for the cotangent, I chose the third one. Maybe at some point in here, I'm like, this is a mess, and this is not working, and I can't figure out what to do next. Sometimes that means that we just start over and we use a different formula, especially if there are different formulas we could use. And that might be a better approach for you, okay? So don't always think that just because you've started one way, you have to finish it that way. You could start all over and do something completely different.